professor at University of North Dakota in chemistry and biochemistry department. And I'm a member of the ACES project, NSF funded project at NDSU. And I belong to the computational pillar. So this is actually the area where we do computational research, which will support experimental data, interpret experimental data, and get into the atomistic understanding of mechanisms, processes which are taking place at the biointerfaces, the processes which are related to the cancer diagnostics and cancer growth, in particular in the bones. So our computational part is important because of two reasons. One, we can get explanation to the things which is hard, if not impossible, to answer experimentally. Because some things really cannot be probed on the experimental level or cannot be checked directly through the experiment. Computations allow for extracting this information just from simulations, from computing models, and using knowledge from experiment, using some data from experimental measurements. We can really explain the trends, we can explain the behavior, we can explain the overall processes, which of course important because we just don't want to know the facts. We want the science goes beyond just getting the facts. The science should explain why this or that phenomena is happening and how we can control this phenomena. To control, we need to know why, what, and how. Without this, control is impossible. So this is the one thing which computations can provide a great benefit to the research in general. And the second part is we not just can interpret the data which were already obtained by experimentalists, we also can provide some predictions about the things which were not measured before. We can predict the behavior, we can predict the structure of materials with specific behavior, and then just navigate the new probes, new experimental probes to check whether our computational predictions are correct or not, which of course will save a lot of time when experimentalists don't need to try many different ways to figure out whether it's really possible or not. They can just go through our guidelines coming from the computations to predict completely new things and completely new materials. So on one hand, we can get more deeper for explanation the things which were measured experimentally. On the other hand, we can get new predictions and guide the experimental probes, guide experiments which can be designed for this and that materials. So since we talk about these biointerfaces, I just will give a little bit more information about biointerface, what exactly we mean by that. In particular, my research group, we are trying to model the biological clays. The clays, it's minerals which are pretty compatible with biological tissues, which can be inserted inside the bones and can be used as a material for growing the bones, or actually helping the bond to reconstruct. But clay by itself is not enough, because really to make it be biocompatible, we need to know how the biological polymers, such as proteins, enzymes, interact with the clay, and whether this type of interaction is similar to the actual real bond and the same protein interaction. So this interface between the biological polymers, proteins, amino acids, and the clays, this is what we want to model and understand the type of interaction and compare with real materials, I mean biological materials such as bonds and the biological polymers. We do this with so-called first principle calculations. And it also means that we rely on the quantum mechanics, on a quantum rather than classical physics. So on one hand, it gives us really more accurate way to predict this processes, interactions between the clay and the biological materials, biological proteins. On the other hand, because it's really very advanced methods, we have to reduce the size of the system. So the systems which we are simulating are typically much smaller, much smaller, comparing to the experimental samples. But even with these small models, with the small size computational models, we still can get very valid, very important information, in particular about the charge distribution due to this interaction between the clay and the polymers. And then this information can be used as a parameters for other type of simulations, which doesn't involve quantum, but just classical simulations, and then can be applied to much bigger system, more comparable to the real systems which are used in experiment. Use it as a parameter, which means we can improve the overall methodology, which can then be directly compared with experimental data. Since we work with computers, the great benefit of computation is that you really don't need to be exactly in the lab. You can do it remotely. You just need the account. You need to get access to the computer where we do the calculations, to the software which we use for these calculations. And with this, you can do it remotely. This was a great benefit, especially during COVID time. So most of our students didn't really lost any hour for their research, because they can do this research really at homes. And it's very different, of course, comparing to when you have to come to the lab and do real experiments, because you cannot do experiments at home. Computations you can, but of course you need training. So we provide this training. We can do it online, as I've already said. Mostly we just need really to get the your NDSU accounts, and this NDSU account will be like email, will allow you to get the account on our NDSU facilities, computational facilities, CCAST. And then with this, we will train you how to use these high performance computing facilities, how to use the software, which is also available on these facilities. And then after this training, most of the work can be done just by yourself. So from this point of view, I think it should be very, very attractive to students who might not really have a lot of time to spend in the lab or really come to the lab. So of course, it's better to do some person interaction in the beginning, because learning processes usually goes much quicker and more efficient when we really have this connection to each other. But again, it really depends on the situation, on the student. We can make even this training through the Zoom, through the internet and remotely. And then most of the part of this research can be completely done remotely. So what also is very beneficial in this research to students, so it's very multidisciplinary research. It's not just focused on the biomedical applications or whatever, biochemistry, biomedical, biotype applications, which is of course a very hot topic now, and probably it's also very attractive to students. But in addition to this focus to the biomedical, biochemical, biological, biophysical applications, it also will provide a lot of new experience to students working with computers. As I already mentioned, high performance computing system using a Linux operating system, which is very different from regular Windows machines, which students usually are working. And so this knowledge is useful not only for science. For example, Linux operating system is a basic system which people use in countings, in business, and so on, in banks systems, and so on. So we will provide this additional experience working with this high performance computers, with a software, computational software, which we use for modeling of materials. Plus, of course, the science effect, science impacts on overall important problems which society is having, such as cancer, problem of cancer, which our research can contribute for the solution.